Let's see, last time we were talking about, or we introduced the idea of Euclidean norm and Euclidean domain. And you can think of a Euclidean domain, that's a place where you have a division algorithm. And it's a fairly powerful thing, right? If you have a Euclidean norm, right, if you're in a Euclidean domain, then you're able to conclude that you're in a principal ideal domain, right? Euclidean domains are principal ideal domains. That was sort of our main theorem that we had from last time. Right, so Euclidean domains are principal ideal domains. The proof, right, once you have this division algorithm, the proof goes exactly like it did when we worked with the integers, right, when we had a division algorithm. It worked exactly like when we were working in f bracket x, right, so it really generalized both of those two proofs. And so our main examples of Euclidean domains, right, we had Z, where the Euclidean norm is just absolute value. We have f bracket x, where the norm of a polynomial is just the degree of the polynomial. And then we had this new example, well, I mean, not new example, but a new place where we were able to finally show that this is a principal ideal domain, right? And the way that works is the norm of a plus bi. Remember, a plus bi is a complex number, and the norm, right, is really just the modulus squared of this complex number. This one was a little bit tricky to actually show that this is a Euclidean domain, but once you do that, right, then you're able to, and I'll write this down, you're able to conclude that we have a principal ideal domain right here, Z bracket I. So a couple of things I want to write down. So, well, first let's write it like this. So this is a corollary. So let's be corollary 46.2. If D is a Euclidean domain, then D is a unique factorization domain, right? And there's nothing to prove here. So what we have, and here, or if you like, here's the proof, right? So Euclidean domain implies principal ideal domain, and then principal ideal domain implies unique factorization domain. And then it turns out that it does not go backwards. UFD does not, there exist UFDs that are not principal ideal domains. And the example, who's our example here? It is Z bracket X, right? We know that Z bracket X is the UFD. The reason is that Z is a UFD. We know that it's not a principal ideal domain. We did an example a week or two ago that showed that Z bracket X is not a principal ideal domain. It turns out that the reverse implication does not go backwards here either. Right? There exists a principal ideal domain that is not a Euclidean domain. That's actually a harder thing to show, and I'll show you I'll give you the counterexample later on. So for now, let's just leave that, and but we'll come back to that. So it turns out then that the converses in any of these directions is not true. Right? And so here's a way to remember it. It goes in alphabetical order, right? Euclidean domain implies principal ideal domain, which implies UFD, but not in reverse alphabetical order. Oh, and I guess I should just write this down for effect. So Z, not for effect, but just for completeness. So Z bracket I is a Euclidean domain. And so what does that tell us then? Right? And so is a principal ideal domain, which means that it is a UFD. So to repeat ourselves, say, and so is a UFD. Now, there's a little bit more, we can get a little bit more mileage out of Euclidean norms. So this next result, so theorem 46.3, so let's let D be a Euclidean domain with norm nu. Two parts of this theorem. So first of all, the norm of 1, it's equal to the min of nu of A, where A runs through all non-zero elements. So what you can view it this way. This part A is saying that the norm of our unity element is minimal amongst all elements of D star, right? And then part B, nu of A equals nu of 1 if and only if if and only if A is a unit of capital D. And so this is nice. What this does is it gives us a way to detect units within a Euclidean domain. What do? You figure out what the norm of 1 is, and then anybody else that has the norm of 1 has to be a unit. Right? So this gives us a nice way for unit detection. So we get a little bit more, right, than just a Euclidean algorithm out of Euclidean norms. I keep saying Euclidean algorithm, sorry. You get a little bit more than a division algorithm out of Euclidean norms, right? You also get this property right here. Okay, so let's prove this. So for part A, there's really nothing to do, right? Yeah, so let's let little a be in D star, right? So then the norm of 1 has to be less than or equal to the norm of 1 dot A. That was property, the second property of Euclidean norms, right? And then this is equal to is that what I want to say? Oh yeah, which is equal to, sorry, equal to not norm of 1. That's equal to the norm of A. Right? So that tells us then that the norm of 1 has to be less than or equal to the norm of every other non-zero element in there, which tells us then that the norm of 1 is minimal amongst all elements of D. Sorry, D star. Okay, so now for the proof of part B, forward direction. So let's assume that the norm of A matches the norm of 1. So so let's assume that norm of A equals norm of 1. And now we want to show that A is a unit. So what I'm going to do is run the division algorithm on it. So by, I mean, I need to put this in quotes. It's not officially the division algorithm, but it behaves as if, or behaves just like the thing that we call the division algorithm. So let me just put it in quotes. So by the division algorithm, algorithm for D, we have, so I want to write 1 is equal to AQ plus R for some Q and R in D, where either R equals 0 or the norm of R is strictly less than the norm of A. All right, so now what? Well, the norm of 1 is minimal amongst all elements, all non-zero elements of A, of D. which tells us that the norm of A is minimal amongst all elements of D star. So what are our options? We can't have any element whose norm is strictly less than R, strictly less than A, which forces us to conclude that R equals 0. All right, so by minimality of the norm of A, we conclude that R equals 0. So what does that tell us then? It tells us that A times Q is equal to 1, right? So since AQ equals 1, we see that A is a unit, right? So anytime, if your norm matches the norm of 1, guaranteed you're a unit. In the reverse direction, let's see if I can squeeze it into this little section here. So let's see, yeah. So if A is a unit, then, well, okay, so then what do we have? 1 is equal to A times A inverse. And so, the norm of, what am I trying to do now? I want to show that the norm of A equals the norm of 1, right? So, right, so the norm of A is less than or equal to, this is our multiplicative property, less than or equal to the norm of A times A inverse, which is less than or equal to the norm of 1. By minimality now, we know that the norm of A cannot be strictly less than the norm of 1. So by minimality of norm of 1, we conclude that the norm of A has to equal the norm of 1. Okay, so this tells us that this idea of Euclidean norm, right, is nice. Not only does it give us a Euclidean algorithm, I keep saying Euclidean algorithm, there's a reason for that, you'll see in just a second. Not only does it give us a division algorithm, right, but it gives us a nice way to detect units within our Euclidean domain. So let's look at some examples now. Well, we have exactly 3 examples of Euclidean domains, right? So the units of Z are those for which the absolute value of n is equal to the absolute value of 1, which equals 1. Well, in Z, that tells us then that n has to be plus or minus 1. So n equals plus or minus 1. So what do we have then? The units of Z, we already knew this, of course, but now we've got a nice proof using Euclidean norms, right? The units of Z are exactly plus and minus 1. Next example, the units of f bracket x are those for which the degree, let's say, of f of x is equal to the degree of 1, right, which we know is 0. So the units are those polynomials that have degree 0, which we know, of course, are the non-zero constant polynomials. So we can say thus, and once again, we already knew this, the units of f bracket x are those, let's say, the non-zero constant polynomials. Okay, so we already knew this, but now we've got a nice proof, all right, using Euclidean norm on f bracket x. And then one more example that we have. So let's see, the units of z bracket I are those a plus bi in z bracket I for which a squared plus b squared, right, that's the norm of a plus bi, is equal to the norm of 1, right, which is 1 squared plus 0 squared, which equals 1. Thus, the units of z bracket I, okay, so if I have an a squared plus b squared equals 1, that tells us that, and we're working with the integers, that tells us that a has to be plus or minus 1 and b equals 0, or a equals 0 and b equals plus or minus 1. So that tells us the units of z bracket I are, well, let's just list them out here. So they're plus or minus 1 and plus or minus I. So there's exactly 4 units in z bracket I. Now, there's one more thing, and I'm not going to prove this, but there's one more fact about Euclidean norms or Euclidean domains. So I'm going to state this is a theorem, but this is one that I'm not going to prove, and we're not going to make use of it. So theorem 46.4. So if D is a Euclidean domain, then there is an algorithm producing a let's say a GCD of every pair of non-zero elements of capital D. And I think I defined GCD either last lecture or maybe the lecture right before, right, when we were talking about if D is a UFD, then D bracket X is a UFD, right? So there's this generalized notion of greatest common divisor. And so in a Euclidean domain, there's a way to actually do this, right, to produce it. And in fact, so we can say moreover, if, let's say, yeah, if D is a GCD of, let's say, A and B in D star, then this algorithm I'm going to say produces. Yeah, produces. Elements, say S and T in D, such that D is equal to AS plus BT. Right, so that's one thing we know about integers, right? Anytime the greatest common divisor can be expressed as a linear combination, right, of the two elements, the two numbers that you're talking about. And okay, so and I said I kept slipping and I kept saying Euclidean algorithm when I meant to say division algorithm. But part of the reason is because this algorithm that exists for Euclidean domains is called a Euclidean algorithm, right? So there is a Euclidean algorithm for any Euclidean domain, right? And what it does, you run this algorithm, and it's essentially just sort of repeating, and you do some, you run the division algorithm, do some subtraction, run the division algorithm, you just sort of iterate that until eventually you get a GCD, right? So that algorithm is called the Euclidean algorithm. I don't want, the proof is this is maybe the one algorithm and proof that I really don't enjoy, right? It's just kind of tedium. You can look in the book to see how this algorithm actually works, right? But this is one that I'm just not I've never been a fan of the Euclidean algorithm for some reason. Okay, so that's it for this chapter. And so I want to start the next one. So this is chapter 47, and this is called multiplicative norms. Right, so what we saw is that having a Euclidean norm on your integral domain, that's very powerful, right? You can say a lot about a Euclidean domain. Now what we're going to do, this thing called multiplicative norm that I'm going to introduce in a second, it's going to allow us to study a certain type of ring, let's just say. Leave it at that for now. So let's let n be an integer. And I want to define, we've seen this we've seen examples of this before. So let's define z bracket square root of n. And it's equal to the set of all things of the form z plus square root of n, where a and b run through all of z. Right? So we've seen this, or at least seen objects like this. We've constructed rings like this before. Now, you can run the subring test. We could say you can use the subring test to show that z bracket square root of n is a subring of C, right? So what we just did then is we created a whole class, a whole new class of rings, right? Things of this form right here. A few observations here. So, somebody need me? Who is that?
Yeah, Tom.
Hey, what's up? Hold up. Someone's out front, so I'm going to pause my video here. Okay, sorry, that was a little interruption, but you know, when you don't see people for a long time, then they stop by my office. So that was Brussel. He just was coming to pick up some book. Fix my camera here. He was coming to pick up a book, and then so I just chatted with him for a little bit. So now I need to remember what I was saying or doing. Oh, I was about to say there's some observations here, right? So, sorry, I just got to get my head back. So, a few observations. Just thinking about this ring right here. So, if n is a perfect square, all right, so this is for some a and z, then, okay, so fine. If you put a squared in here, then what you're going to get is z bracket some integer. So then z bracket square root of n is just the integers, right? So there's nothing exciting there. Oh, right. Now we have seen this actually explicitly in one case. So the next thing, when n equals -1, then z, right, so z bracket square root of -1 is the same as z bracket I. And then, one more observation. No matter what, z bracket square root of n is an integral domain. And the reason, well, it's a subring of a field, which is an integral domain, right? So by virtue of being a subring of C, that tells us that all of these, for any choice of n, we have an integral domain. So this is because C is. All right, so there's just a few things to observe. Okay, now what we want to do is we want to study the properties of these rings right here. And here, so I want to say this, to study properties of Z bracket root n. In particular, we really want to study divisibility or factorability here. So especially what we want to do is understand the nature of primes and irreducibles. And other things, but those are the main two things. So we introduce the following. So this is going to be a definition here. So now let's just let D be an integral domain. A function which we're going to use a capital N from D to the integers is a multiplicative norm on capital D if two properties hold. So first of all, the norm of A equals 0. I want to say if and only if. Yeah. So norm of A equals 0 if and only if A equals 0. And the second property is that n of A times B is equal to n of A times n of B for all A and B in D. There's the multiplicative part right there, right? So multiplicative norm is one that only sends A to 0 in the case that A is 0, or so you can say it this way, it only sends A to 0. And secondly, it satisfies this multiplicative property right here. Now, how are we doing on time? Yeah, okay, so let's prove one thing about this, or one theorem. It's actually got 3 parts, so it'll take me a little bit of time, but so theorem 47.1 goes like this. So let's let capital N be a multiplicative norm on capital D. So then, so 3 things are true. So first of all, a multiplicative norm takes the multiplicative identity to the number 1. All right. Remember, a norm goes from D to 1. So here, in fact, let me write this as just my usual numeral 1. Right. So it takes the multiplicative identity, the unity element, to the number 1. Part B. So part B, n of u equals 1 for every unit u in D. Right? So it takes the unity element to 1, it takes every unit to 1. And then the third part goes like this. This is kind of a mouthful here. So if oh, and I just screwed this up. Sorry. I need absolute value right there. Right? So it takes a unit, the norm takes a unit to plus or minus 1, right? So absolute value of 1, absolute value of the norm of every unit is 1. And then the last thing here, so if the absolute value of the norm of, let's see, we'll go in here, we'll say A equals 1 only when A is a unit, then the following holds. So then the following holds. If the absolute value of the norm of A is prime in Z, then A is an irreducible of capital D. So, okay, so what do we have here? Takes unity to 1, takes the absolute value of every unit is 1, and then this last part here is kind of curious. So what this says, or if you look up at part B, it's saying that units have to go to plus or minus 1, but it doesn't tell us anything else. So it's possible that non-units could have absolute value equal to 1 also. However, if your norm is such that the absolute value of the norm is equal to 1 only for units, then this nice property happens. It allows us to detect irreducibles, right? If the absolute value of the norm is prime, a prime number in the integers, right, then we can conclude that A is irreducible. Okay, so let's prove these. So proof of part A. Okay, so we got to show that the norm of 1. So the norm of 1 is equal to, right, okay, so it's equal to the norm of 1 times 1, which is the norm of 1 times the norm of 1. And so what do we have? The norm of 1 is equal to the square of the norm of 1. So we can conclude, so the norm of 1 is equal to 0, or norm of 1 is equal to 1. But by our previous property, I guess that's property 1 of multiplicative norms, right, is that only 0 can go to 0, right? So by property 1 of multiplicative norms, right, so this is right from the definition, we have, right, this one can't happen, and so it's got to be this one. So we have norm of 1 equals 1. Okay, so part B, now we want to show that the absolute value of norms has to be equal, of units has to be 1. So so let's let U in D be unit. Then what do we have here? 1 is equal to the norm of 1, which is equal to the norm of U times U inverse, which is equal to the norm of U times the norm of U inverse. So now what we have is, and we know, right, norm of U is an integer, norm of U inverse is also an integer. So we have a product of two integers equal to 1. That's only possible if both of these are plus or minus 1. So we can say, and so the norm of U is equal to plus or minus 1, which means then that the absolute value is equal to 1. Okay, so now the last one, right? If the norm, absolute value of the norm, goes to 1 only when we have a unit, then we get to use this to detect irreducibles. So let's assume, so let me write it like this. So this is the proof of C. So assume that the set of all A and D such that the absolute value of the norm of A is equal to 1 is equal to the set of all units of D. Now, okay, so choose X in D, where the norm of X in absolute value is a prime number, right? So it's equal to P, where P in Z is prime, right? So now our goal is to show that X has to be an irreducible. So suppose that that X is equal to, let's say, A times B, right? For some A and B in capital D. Right, so now what do I need to do if I want to conclude that X is an irreducible? Then I need to show that A is a unit or B is a unit. Okay, so then we have that P is equal to the norm of A times B, right? Because that is the norm of X, or X is A times B. So that's equal to the norm of A times the norm of B. Oh, sorry, and I lost my absolute values there. That's equal to that, which is equal to, okay, let me do one more step. That's absolute value norm of A times absolute value of norm of B. So now what do we have? We have P written as a product of these two right here, right? Well, what are the possible factors? One of these has to be the number 1, where the other one has to be P, right? So it follows that absolute value of the norm of A equals 1, or absolute value of the norm of B equals 1. And so what did we say up here? We assumed that you only get an output of 1 absolute value, right, if you're a unit. So A is a unit, or B is a unit. Therefore, X is irreducible. Okay, so that completes the proof, and this is a good place to stop. So we're going to see how to make use of this multiplicative norm business in our next lecture. All right, see you then.